Hello and welcome, curious dreamer. You found your way back to the Sleepy Scientist, where we drift through the cosmos, time and the wonders of the natural world, one gentle thought at a time. Tonight, we're gliding back into Earth's deep past, to an era when the entire planet may have been blanketed in ice. It's a tale of glaciers, ancient snowstorms, and a world that very nearly became a frozen marble floating through space. But before we bundle up and venture into the frost, I'd love to know, where are you listening from tonight? And what time is it in your corner of the world? Whether it's the dead of night or just after dinner, I hope this journey keeps you company. And if you find yourself enjoying this gentle stroll through time, please consider tapping the like button or even subscribing. It helps the channel grow and makes sure you don't miss our next sleepy exploration. Now, I should warn you, I've done my best to make this video calm and relaxing, but I may have accidentally made it a little too interesting. So if you do stay awake, hopefully it's because you're learning something fascinating. And if you drift off halfway through, well, that's perfectly all right too. The glaciers will still be here when you wake up. What exactly is an ice age? It's the sort of term we all grew up hearing in documentaries and cartoons, often featuring woolly mammoths slipping on ice or cavemen wearing suspiciously well-tailored furs. But behind the frosty drama lies a surprisingly nuanced and deeply fascinating idea. An ice age isn't just one long winter, or even a particularly snowy decade. It's a prolonged period, millions of years in some cases, when Earth's climate is cool enough for ice sheets and glaciers to form and stick around, especially at the poles. And believe it or not, we're living in one right now. Yes, you heard that right. Despite your summer tan and the lack of saber-toothed tigers in your local park, we're technically still in an ice age. More specifically, we're in an interglacial period, a warmer phase within a much longer ice age that began around 2.6 million years ago. So the next time someone says we've left the ice age behind, you can gently raise an eyebrow and say, actually, we're just enjoying a temporary thaw. To understand how this works, let's start with the basics. Earth's climate isn't fixed. It changes, sometimes subtly, sometimes dramatically. These changes happen over many different timescales, from a few years, thanks to volcanic eruptions or ocean currents, to tens of thousands or even millions of years, thanks to orbital wobbles, tectonic shifts, and greenhouse gas levels. Ice ages are one of the grandest, most epic of these long-term shifts. They are like climate's deep breaths, in and out, cold and warm. The hallmark of an ice age is the presence of large ice sheets covering continental landmasses. Not just a few snowstorms or seasonal frost, but vast, grinding, mind-bendingly heavy rivers of ice, stretching over huge parts of the globe. During the peak of the last glacial period about 20,000 years ago, glaciers covered much of the North America, Europe, and Asia. Sea levels were over 100 meters lower than they are today, exposing land bridges between continents and reshaping the way animals and humans migrated across the Earth. But here's where things get a little more technical. Within an ice age, climate naturally oscillates between colder glacial periods and warmer interglacial periods. Think of it like a natural pulse: freeze, thaw, freeze, thaw. These shifts happen over tens of thousands of years, driven by a mix of cosmic nudges and planetary feedback systems. During glacial periods, massive ice sheets expand and sea levels drop. During interglacials, those ice sheets retreat and the world warms up a bit, like what we're experiencing now. To date, Earth has seen at least 5 major ice ages. The earliest known one was over 2 billion years ago, during a time when life on Earth was still mostly microscopic and unbothered by things like snow boots or central heating. The most recent and best studied is the Quaternary Ice Age, which began around 2.6 million years ago and continues today. It's in this most recent icy epoch that the human story truly begins. But ice ages don't happen randomly. They're triggered and shaped by a complex interplay of factors. One major player is the amount of carbon dioxide and other greenhouse gases in the atmosphere. When levels drop low enough, the planet starts to cool. But greenhouse gases are just one part of the puzzle. The shape of Earth's orbit around the Sun also has a major influence. It wobbles slightly over time, tilting, stretching, and precessing in predictable cycles known as Milankovitch cycles. These slow astronomical shifts affect how sunlight is distributed across the planet, especially in the polar regions. If the timing is just right, they can tip the climate toward glaciation or thaw. Then there's the role of the continents themselves. Over geological timescales, continents drift around the globe like lazy icebergs. When land masses move toward the poles, it creates space for ice sheets to grow. When ocean currents shift due to tectonic changes, it can dramatically alter how heat is moved around the planet. In other words, where your mountains and seas are located matters a lot to the thermostat. And once ice starts to accumulate, it tends to encourage even more of itself. This is thanks to something called albedo, a measure of how much sunlight a surface reflects. Ice and snow are very reflective, bouncing sunlight back into space and helping the planet stay cool. So the more ice you have, the more the planet reflects heat and the colder it gets. It's a frosty feedback loop that can spiral into some seriously chilly consequences. But ice ages aren't just about frozen landscapes and geological mechanics. They've had a profound effect on life itself. Glaciations have repeatedly reshaped the Earth's ecosystems, pushing species to adapt, migrate, or perish. Entire landscapes have been sculpted by glaciers, carving out valleys, grinding down mountains, and leaving behind the fingerprints of ice across every continent. In many ways, ice ages are nature's way of hitting the refresh button. They clear the slate, shuffle the deck, and set the stage for evolutionary bursts and new ecosystems. Without ice ages, humans might never have left Africa. Woolly mammoths might never have existed. Your cozy valley town might still be buried under kilometers of ice. So the next time winter overstays its welcome and you're cursing the frozen sidewalk, take heart. It's all part of a much, much larger story. A story that stretches back millions of years and connects geology, astronomy, biology, and the very evolution of life on Earth. And that's what makes ice ages so deeply compelling. They're not just frozen footnotes in history. They're the slow, patient rhythms of a living planet. Cold, yes. Harsh, sometimes. But also deeply beautiful. They remind us that Earth is never truly still. It breathes, shifts, freezes, and thaws, all in time with forces far bigger than any weather report. So tonight, as you sink deeper into your pillow, let your thoughts drift, not just to frozen tundras and icy mountains, but to the quiet power of deep time, and the comforting thought that, through all its ages and upheavals, Earth keeps turning, ice and all. Imagine Earth, not as we know it, with busy cities, green forests and blue oceans, but as a frozen sphere locked in ice from pole to equator, a white marble drifting silently through space. No gentle waves lapping at tropical shores, no green leaves fluttering in the breeze, just glaciers stretching endlessly across continents, and a sea encased in a shell of ice thick enough to bury mountains. This is the world of Snowball Earth, one of the most extreme climate events our planet has ever known. It sounds like science fiction, but it's one of the most intriguing ideas in modern geology. And the best part, it likely happened more than once. Let's set the stage. We're traveling back in time, way back, hundreds of millions of years before dinosaurs, before ferns, before even the first complex animals crawled across the seafloor. The planet was still young in many ways, with life just beginning to experiment with complexity. Most living things were single-celled, floating quietly in ancient oceans that covered much of the globe. There were no trees, no fish, and definitely no humans, just bacteria, algae, and other tiny pioneers. Now, sometime around 720 million years ago, something changed. The climate began to cool, slowly at first, then more dramatically. Ice began forming at the poles, then creeping outward across the continents. The cooling accelerated, and soon glaciers were rolling over the land, carving out valleys and piling up like bulldozers made of frozen time. The oceans too began to freeze, not just the surface, but possibly hundreds of meters deep. And then, silence. Earth was sealed in ice. The evidence for this comes from rocks. Yes, rocks can tell stories, especially glacial ones. All over the world, geologists have found layers of rock that look suspiciously like those formed beneath glaciers. These are called tillites, jumbles of broken stone and debris deposited as ice flows melt. What's strange is that we find these glacial deposits not just near the poles, where you'd expect them, but in what would have been tropical zones at the time. Places like Namibia, Australia, and the Congo. How could that be? The only way for tropical glaciers to make sense is if the entire planet was cold, really cold. Another clue comes from dropstones, large chunks of rock that seem out of place, sitting in fine-grained marine sediments. These rocks likely hitched a ride on icebergs, which floated out over the ocean and melted, dropping their rocky cargo into the soft seafloor mud. When scientists date these rocks and analyze their magnetic orientation, they find they were deposited near the equator. In other words, there were icebergs in the tropics. That's not just a cold snap, that's a planetary deep freeze. So how did it happen? Scientists believe it may have started with a series of unfortunate coincidences. First, the supercontinent Rodinia was breaking apart. This exposed lots of fresh rock to the atmosphere, which tends to soak up carbon dioxide, a key greenhouse gas. With less carbon dioxide, the planet began to cool. Second, Earth was receiving slightly less energy from the sun than it does today. The sun back then was younger and a little dimmer. Add in a few well-timed volcanic eruptions which can release reflective particles into the upper atmosphere, and the stage was set for a sudden slip into snow and silence. Once glaciers began to spread, they may have triggered a feedback loop known as ice albedo feedback. Here's how it works. Ice and snow are excellent reflectors. They bounce sunlight back into space, preventing that energy from warming the planet. So the more ice you have, the more sunlight is reflected, and the colder the planet becomes. And the colder it gets, the more ice forms. It's a runaway process, one that could, under the right conditions, lead to a nearly frozen planet. But was Earth really frozen solid? That's where the debate begins. Some scientists think the term snowball Earth might be a bit dramatic. Instead, they suggest a slushball Earth, a planet still mostly frozen, but with thin patches of open water near the equator where some sunlight could sneak through. These thin blue ribbons may have been enough to keep life going, barely. After all, even during the coldest times, bacteria and algae likely survived in pockets of liquid water, perhaps in geothermal springs under the sea ice or near undersea volcanic vents. This brings us to a question that's both fascinating and eerie. If the whole planet was frozen over, how did life survive? And not just survive, thrive afterward. One idea is that these extreme conditions may have acted as an evolutionary pressure cooker. Life was pushed to its limits, forced to adapt, evolve, and innovate. After each snowball episode, when the ice finally melted, Earth experienced a burst of biological creativity. Some scientists even suggest that these deep freezes helped pave the way for multicellular life and eventually animals. But what about the thaw? How did Earth escape its icy prison? The answer, once again, lies in carbon dioxide. During the snowball period, with most of the planet covered in ice, weathering processes that normally remove carbon dioxide from the atmosphere would have slowed down or stopped. But volcanoes? They kept going, belching out greenhouse gases like clockwork. With nowhere for the CO2 to go, it built up in the atmosphere over millions of years, like a slow-motion pressure cooker of warming. Eventually, the blanket of greenhouse gases grew thick enough to trigger a dramatic global warming. Temperatures soared, glaciers retreated, and Earth swung from an icebox to a hothouse in geological terms. Some scientists think the resulting melt may have caused massive flooding and extreme weather, perhaps the wildest spring break the planet has ever seen. And after that, warm oceans, rich chemical soups, a world reborn. It's possible that these post-snowball conditions helped set the stage for the rise of complex life, leading eventually, very, very eventually, to everything from trilobites and trees to humans and house cats. It's a humbling thought, really, that our warm, comfortable world with its oceans and seasons and breathable air is the result of a long and dramatic history filled with chaos, cold and quiet endurance. A planet that nearly froze to death, but didn't. So next time you're watching snowflakes drift past your window or sipping tea under a thick blanket, remember, Earth has seen colder days, much colder. And through all the freezing, thawing and frozen silence, life found a way to carry on. Tiny, tenacious, and utterly unstoppable. It's hard to imagine a planet locked in ice ever warming again. When Earth enters a deep freeze, like the kind we saw during the Snowball Earth episodes, it's not just a little chilly. It's catastrophically, comprehensively cold. The oceans are frozen over, the continents are buried in glaciers, and sunlight is mostly bouncing right off the icy surface and back into space. From a distance, Earth would look less like the blue marble we know and love, and more like a frosted glass ornament, cold, shiny and still. So how exactly did we escape? The answer, surprisingly, comes from deep underground. Even during the most dramatic glaciations, the planet never really stops moving. Beneath the ice, the mantle churns, tectonic plates drift, and volcanoes do what they've always done, erupt. While Earth's surface may have been frozen in silence, its interior was still very much alive. Volcanoes became the unlikely heroes of this icy epic. As they erupted, they released carbon dioxide into the atmosphere, a lot of it. Under normal, non-frozen conditions, carbon dioxide is pulled from the atmosphere by a process called chemical weathering. Rain mixes with the gas in the air, forming weak carbonic acid, which then reacts with rocks. This process helps sequester carbon and regulates Earth's climate over long timescales, But during a snowball Earth, that system effectively shuts down. There's no rain on a frozen world, no flowing rivers, and the rocks are buried beneath snow and glaciers. That means all the carbon dioxide from volcanic eruptions just accumulates, slowly, patiently, over millions of years. Picture it like this. Earth is building itself a greenhouse, one tiny puff of volcanic gas at a time. The ice reflects sunlight, keeping temperatures low, but with nothing to remove the accumulating greenhouse gases, the planet is caught in a long, slow warming trap. Eventually, the concentration of carbon dioxide gets high enough to overcome the icy feedback loop. The planet begins to warm. And when it starts, it doesn't stop gently. Oh no! It swings in the opposite direction with almost theatrical flair. Some scientists estimate that carbon dioxide levels at the end of a snowball Earth period may have reached hundreds of times what we see today. When the ice finally began to melt, it did so rapidly, unleashing a cascade of environmental change. Glaciers retreated, oceans thawed, massive floods lightly swept across the continents, carving out landscapes and carrying huge loads of sediment into the seas. With the melting came runoff filled with minerals and nutrients, which poured into the oceans and fertilized the ancient seas like never before. This sudden nutrient boost may have played a critical role in waking up the biosphere. Algae and cyanobacteria, long confined to surviving in narrow pockets of liquid water beneath the ice, now found themselves in a world of opportunity. Sunlight poured into the oceans, nutrients swirled through the currents, and life responded with a flourish. Some researchers even believe that this post-glacial bloom helped pave the way for the rise of complex multicellular organisms. In other words, the ice that nearly snuffed out life may have, in a strange twist, prepared the stage for life to evolve in bold new ways. It's worth noting that Earth didn't just thaw once. There were likely two major snowball Earth events during a time period known as the Cryogenian. First, the Sturtian glaciation, around 720 million years ago, and then the Marinoan, around 630 million years ago. Each may have lasted for tens of millions of years. That's a lot of time to be frozen, and a lot of time for volcanic gases to build up. After the Marinoan episode, Earth entered a much warmer and more stable period known as the Ediacaran. This is when we begin to see the earliest traces of large, soft-bodied organisms in the fossil record. They were strange, alien-looking creatures, frond-like forms pressed into ancient seafloors. We're not entirely sure what they were. Some might have been early animals, others some evolutionary dead ends, but what's clear is that life had taken a leap forward. The idea that cataclysmic ice could lead to evolutionary progress is both fascinating and a little poetic. It suggests that life doesn't just endure hardship, it transforms through it. Pressure, as they say, makes diamonds. And in the case of snowball Earth, cold made complexity. But returning to the physical planet itself, the transition from a snowball state to a warmer climate wasn't just a biological revolution, it was a geological and atmospheric one too. As the ice melted, the land exposed underneath began weathering again, sucking carbon dioxide back out of the air. Over time, this would help stabilize the climate, drawing down the intense greenhouse gases and eventually restoring balance. The water cycle resumed, rivers flowed again, storms rolled across the sky, Earth had reawakened. Interestingly, this wild swing from frozen silence to roaring warmth is one of the reasons why snowball Earth is still debated among scientists. Some suggest that the full globe freeze was unlikely and instead propose a slushball Earth, where some equatorial oceans remained unfrozen, allowing more continuity for marine life and perhaps moderating the rebound warming. It's a subtle distinction, but an important one, as it changes how we think about Earth's climate sensitivity and the resilience of early ecosystem. Still, even the most conservative models agree, something profound happened in the Cryogenian period. Whether it was a total snowball or a patchy slush ball, the planet endured one of the most extreme climate swings in its history, and life not only survived, it set the stage for all future complexity. The irony, of course, is delicious. The very thing that nearly wiped out life may have been the spark that helped it flourish. Earth, in trying to destroy itself with cold, may have given life the evolutionary nudge it needed. And it did it not through chaos alone, but through cycles, chemistry, and the slow grind of geology. So next time you see a volcano quietly puffing away on the horizon, or a glacier gleaming in the sun, remember, these aren't just static features. They're part of a grand planetary ballet, a slow, deliberate rhythm that once brought the world back from the brink of a frozen death. And perhaps, in some far-off way, they helped make everything you know possible. Imagine Earth's continents not as fixed pieces of geography, but as slow-moving rafts drifting atop a sea of molten rock. Over millions of years, they wander, collide, and break apart again in a planetary game of bumper cars played out in extreme slow motion. This is plate tectonics, the subtle but relentless movement of Earth's lithosphere, and it plays a starring role in the grand climate story that includes our planet's ice ages. At first glance, it might not be obvious how the placement of continents could affect something as vast as the climate. After all, how can the slow crawl of land masses possibly influence global temperatures, let alone tip the planet into a deep freeze? But the truth is, where continents are located has a powerful effect on how heat and moisture move around the planet, and ultimately whether ice sheets thrive or wither away. Let's start with something simple: ocean currents. These vast rivers of moving water are like the arteries of the climate system. They carry heat from the equator toward the poles and help balance temperature differences across the globe. But they don't just go wherever they like. They are shaped and steered by the arrangement of continents. When continents move, they change the shape of the ocean basins, which in turn reshapes the currents. A shifting continental position can redirect warm water away from the poles or trap cold water in deep basins, both of which can have dramatic impacts on the climate. Take, for example, Antarctica. Today it's the icy crown of the southern hemisphere, buried under kilometers of snow and home to some of the coldest temperatures on Earth. But it wasn't always this way. Around 35 million years ago, Antarctica began to separate from South America and Australia, opening up the Southern Ocean. This allowed the Antarctic Circumpolar Current to form, a powerful band of cold water that circles the continent and effectively insulates it from warmer ocean currents. As this current strengthened, Antarctica's climate cooled dramatically and glaciers began to form. Before long, it became the frozen landmass we know today. Or consider the Himalayas. These towering peaks were born when the Indian subcontinent slammed into Asia around 50 million years ago, a continental collision that continues to this day. The rise of the Himalayas and the Tibetan Plateau had a profound effect on global weather patterns. Their sheer size disrupts air currents, changes monsoon systems, and increases rock weathering, which draws carbon dioxide out of the atmosphere. That in turn cools the planet. It's like the continents are giant thermostats. Move them to the right places, and you can cool the planet down enough for glaciers to grow. But let's go even further back in time, hundreds of millions of years, to when the supercontinents ruled the Earth. Supercontinents are massive landmasses that form when all or most of Earth's land comes together. They've come and gone several times over the planet's history, with names like Rodinia, Gondwana, and Pangaea. Each one has had its own unique effect on the climate. Rodinia, for example, may have played a key role in triggering the Snowball Earth episodes we explored earlier. Around 700 million years ago, this supercontinent began to break apart. As it did, vast areas of fresh, exposed rock were left to weather under the rain and wind. This rock weathering process pulled carbon dioxide out of the atmosphere, a vital greenhouse gas. With less carbon dioxide, the planet cooled. Add in the fact that much of Rodinia's landmass was near the equator, where weathering is especially effective, and you've got a recipe for planetary refrigeration. Fast forward to Pangaea, the most famous of the supercontinents, which formed around 300 million years ago. This enormous landmass stretched from pole to pole with a vast interior that was dry, desert-like, and far from the stabilizing influence of the oceans. The formation of Pangaea coincided with another major glaciation, especially in the southern hemisphere, where the continent of Gondwana, part of Pangaea, was located over the South Pole. Giant ice sheets spread across what is now South America, Africa, India, and Australia. The positioning of land at the poles is especially important. Ice sheets need land to grow. They can't form in open ocean, at least not in the same vast, persistent way. When a continent drifts over one of the poles, it gives ice a place to accumulate. Once it starts forming, it reflects more sunlight back into space, reinforcing the cold. It's another one of those feedback loops, quietly shifting the planet into a new climatic chapter. But plate tectonics doesn't just affect ice through geography, it also affects the chemistry of the planet's atmosphere. When mountain ranges rise, they expose fresh rock, which undergoes chemical weathering. This pulls carbon dioxide from the air, helping to cool the climate. When continents collide, they can trap organic carbon in the crust. And when volcanoes erupt, often at the plate boundaries, they can inject huge amounts of carbon dioxide back into the atmosphere, warming things up again. It's a long, slow conversation between the Earth's crust and its climate. A push and pull, a gradual negotiation. Over millions of years, these processes shape not just the land, but the skies above it and the temperature of the oceans that lap at its shores. One of the most fascinating things about this interplay between plate tectonics and climate is how indirect it can be. A shift in one continent's position might cause changes in ocean circulation, which affects rainfall patterns, which influences plant growth, which alters atmospheric carbon levels, which affects global temperatures. It's a chain of dominoes, and it might take tens of millions of years to fall. So while it may seem strange to credit mountain building with triggering an ice age, or to blame the breakup of a supercontinent for a frozen equator, that's exactly the kind of cause and effect we see in the deep history of Earth. All of this reminds us that our planet is not static. It is alive, in a slow and majestic sort of way. The continents shift, the oceans rearrange, and the climate responds. Ice ages come and go, not just because of distant stars or invisible gases, but because the very ground beneath our feet is always on the move. And though these movements are too slow for us to notice in a single lifetime, over geologic time they shape the world in ways that are both profound and beautiful. A snow-covered mountain range, a deep ocean trench, a fertile valley carved by ancient glaciers. Each of these tells the story of Earth's restless crust and its quiet but powerful influence on the climate we live in. If you've ever seen Earth's orbit illustrated in a science textbook, you might have noticed that it's often drawn as a neat ellipse, a slightly squished circle with the sun off to one side. That image, while helpful, doesn't quite capture the full elegance of our planet's cosmic choreography. Because Earth's orbit isn't just fixed and predictable, it's in constant motion. It wobbles, shifts, tilts, and stretches. And these seemingly small changes, spread over tens of thousands of years, can determine whether glaciers grow or melt. Welcome to the world of the Milankovitch cycles. Named after Serbian mathematician and astronomer Milutin Milankovic, these cycles are a set of 3 long-term variations in Earth's movements that influence how sunlight is distributed across the planet. Think of them as slow, celestial nudges that adjust the Earth's climate over time, not in dramatic day-to-day ways, but in grand, rhythmic pulses. Let's begin with the first cycle, eccentricity. This refers to the shape of Earth's orbit around the Sun. Right now, Earth's orbit is nearly circular, meaning we're almost the same distance from the Sun throughout the year, but this isn't always the case. Over a cycle of about 100,000 years, the orbit becomes more elliptical, then less elliptical, then back again. When the orbit is more stretched out, the difference in solar energy between the closest and farthest points becomes more pronounced. This can slightly affect how much sunlight the planet receives during different times of the year. Next, we have obliquity, or axial tilt. This is the angle between Earth's rotational axis and its orbital plane. Right now, Earth is tilted at about 23.5 degrees, but over a cycle of roughly 41,000 years, that tilt can increase to nearly 25 degrees or decrease to just over 22 degrees. The tilt of the Earth determines the severity of the seasons. A greater tilt means more extreme seasons, hotter summers and colder winters. A smaller tilt leads to milder seasons. These changes can affect how much summer melting occurs at high latitudes, which is critical in deciding whether ice sheets advance or retreat. The third cycle is precession, which is a fancy way of saying that Earth wobbles like a spinning top. Over a cycle of about 23,000 years, the direction of Earth's axis slowly rotates. This wobble changes the timing of the seasons relative to Earth's position in its orbit. Right now, the northern hemisphere's summer occurs when Earth is farthest from the Sun. But in about 11,000 years, that will reverse. Summer will occur when Earth is closest to the Sun, making it warmer. Now, you might be thinking, these are such small, slow changes. Can they really trigger an ice age? And the answer is, yes, they can, especially when combined. The magic of the Milankovitch cycles is in how they work together. When the orbit is more elliptical, the tilt is small, and the timing of the seasons aligns just right. Summers in the northern hemisphere can become cool enough that winter snow doesn't fully melt. Year after year, that snow builds up, compresses into ice, and begins the slow march of a glacier. Over thousands of years, those glaciers grow into ice sheets that spread across continents, lowering sea levels and transforming entire ecosystems. Why is the northern hemisphere so important in all of this? It's because it has more land at high latitudes than the southern hemisphere, and ice needs land to build up. You can't have a mile-thick glacier floating on the open ocean. So the northern hemisphere's summer temperatures are a key ingredient in the recipe for glaciation. These cycles also help explain the timing of past glacial periods. When scientists drill deep into the Antarctic or Greenland ice sheets, they find layers of ancient ice that contain bubbles of air trapped thousands or even hundreds of thousands of years ago. These layers act like a climate time machine, telling us about past temperatures and atmospheric composition. What they've found is that glacial and interglacial periods appear to follow the rhythm of the Milankovitch cycles, especially the 100,000-year eccentricity cycle. Interestingly, the effects of these cycles are not dramatic by themselves. The amount of solar energy change is relatively small, usually just a few percent. But when combined with other feedback mechanisms like changes in greenhouse gases, ocean currents, and ice albedo effects, those small shifts can tip the climate balance. Let's use an analogy. Imagine the Earth's climate as a giant marble sitting in a shallow bowl. It's stable but not fixed. The Milankovitch cycles act like someone slowly tilting the bowl back and forth. Most of the time, the marble just wobbles around a bit and stays put, but every so often the tilt aligns just right and the marble rolls into a new position, a new climate state. Another key thing to remember is that while these cycles can trigger changes, they don't cause them in isolation. They're more like conductors in an orchestra, setting the tempo for instruments that include carbon dioxide levels, methane, vegetation, sea ice, and ocean circulation. Together, these factors amplify and sustain the climate's rhythm, and sometimes the music changes dramatically. About 20,000 years ago, Earth was in the grip of the last glacial maximum, a period when ice sheets covered much of North America, Europe, and Asia. Sea levels were lower, deserts were larger, and ecosystems looked very different from today. Then, as the Milankovitch cycles shifted, summers in the northern hemisphere grew warmer. Ice sheets began to melt, sea levels rose, forests reclaimed former tundra, and slowly the planet emerged from the cold. Today we're living in what's called the Holocene, a relatively warm interglacial period that began around 11,000 years ago. According to the natural rhythms of the Milankovitch cycles, we might expect Earth to gradually cool again over the next several thousand years, eventually sliding into a new glacial period. But humans have added a new twist to the story. By burning fossil fuels and increasing greenhouse gas levels in the atmosphere, we've introduced a powerful warming force that may override the slow pull of celestial cycles. In other words, the music hasn't stopped, but we've started playing a very loud and unexpected instrument. Still, there's something profoundly calming about the idea that Earth moves in rhythms. These cycles, slow and silent, have guided the rise and fall of glaciers, shaped the evolution of life, and determined the contours of coastlines for millions of years. They're a reminder that while our own lives move quickly, the planet dances to a much slower beat. So as you drift off tonight, you might picture Earth, gently fending through space, tilted just so, tracing its elliptical path around the sun, its seasons changing, its glaciers advancing and retreating, all in quiet conversation with the stars. Let us travel now to a time not so far away, at least not compared to the snowball Earth days. Around 2.5 million years ago, give or take, our planet entered the most recent of its great icy eras, the Quaternary Ice Age. Unlike the deep freezes of the Cryogenian or the great glaciations of ancient supercontinents, this one is far more familiar. It's the age of mammoths and giant sloths, of human ancestors wrapped in furs, of advancing ice sheets that carved valleys and shaped the landscapes we still live in today. This period, stretching from about 2.5 million years ago to the present, has been marked not by a single unbroken chill, but by repeated cycles of freezing and thawing. Glacials and interglacials in a slow, steady rhythm. Glaciers would creep down from the poles, covering huge swathes of North America, Europe, and Asia. Then, after tens of thousands of years, they would retreat, leaving behind scars, lakes, and stories written in stone. Let's focus on the most recent cold chapter, the last glacial maximum. This was the peak of the last glacial period, occurring roughly 20,000 years ago. At that time, vast ice sheets covered most of Canada and extended as far south as what is now the upper Midwest of the United States. Northern Europe was buried under the Scandinavian ice sheet, and thick glaciers spread across Russia and parts of the British Isles. Even the highlands of Scotland, Ireland, and northern England were completely entombed in ice. It's hard to picture just how dramatic this was. Sea levels were more than 100 meters lower than they are today. If you were to visit what is now the English Channel, you could have walked from Britain to France without getting your feet wet. In fact, many parts of the world that are now underwater were dry land, fertile ground for mammoths, reindeer, and the early humans who followed them. Speaking of mammoths, this was their golden age. The woolly mammoth, with its long curved tusks and shaggy coat, was perfectly adapted to the cold, open landscapes of the Pleistocene epoch. Alongside it roamed other Ice Age megafauna, like the woolly rhinoceros, the giant ground sloth, saber-toothed cats, and the massive short-faced bear. These creatures were built for endurance and toughness, living in a world where summers were brief and winters bit hard. But perhaps the most remarkable story of this age is the story of us, humans. Our ancestors lived through the Ice Age, not as passive bystanders, but as active participants in a dramatic and often dangerous environment. They learned to adapt, to build shelters, to control fire, and to craft tools out of stone and bone. Some wore clothing stitched from animal hides. Others painted their memories on cave walls deep in the earth. It was during this time that humans expanded out of Africa and spread across the globe. The land bridges created by lower sea levels allowed them to walk into new continents. One of the most famous of these was Beringia, a vast frozen bridge connecting Siberia to Alaska. Through this icy corridor, early humans likely entered the Americas, beginning a journey that would eventually reach every corner of the continent. Life during the last glacial maximum was not easy. Food was scarce, winters were long, and survival required constant ingenuity. But the cold also created opportunities. The great ice sheets acted like bulldozers, scraping away soil and rock, shaping valleys and leaving behind mineral-rich landscapes. As the ice retreated, these lands became some of the most fertile on Earth, supporting forests, grasslands, and eventually human agriculture. The retreat of the ice began slowly, around 19,000 years ago. Summers in the northern hemisphere grew a little warmer, thanks in part to those ever-reliable Milankovitch cycles, and the glaciers began to melt. Rivers swelled with glacial runoff, carving deep canyons and flooding ancient valleys. Ice dams occasionally burst, unleashing catastrophic floods that reshaped entire regions in a matter of days. One such event happened in what is now the Pacific Northwest of the United States. A massive glacial lake called Lake Missoula would repeatedly form, held back by an ice dam. When the dam failed, which it did dozens of times, it released torrents of water that tore across the landscape, carving the dramatic scablands of eastern Washington in mere hours. It's one of the most stunning examples of sudden, large-scale change in the geological record. As the glaciers retreated, they left behind more than just reshaped landscapes. They also left behind clues, layers of sediment, ancient pollen, and the bones of long-extinct creatures. These remnants help scientists piece together the story of our most recent ice age, offering a window into how climate has changed over time and how life has responded. The melting of the great ice sheets also had a profound effect on sea levels. Over several thousand years, the seas rose by more than 100 meters, flooding coastal plains and submerging land bridges. Islands were formed, coastlines redrawn, and entire ecosystems transformed. Humans living at the time would have witnessed these changes not as sudden disasters, but as slow, relentless shifts in the world around them. Shorelines crept inland, rivers changed course, familiar hunting grounds vanished beneath rising tides. Even today, we live with the legacy of the last glacial maximum. The Great Lakes of North America, for example, were carved out by glacial ice. So were many of the fjords in Norway, the lochs of Scotland, and the broad U-shaped valleys found across Europe and Asia. Our planet bears the fingerprints of ice everywhere, etched into the land like a story waiting to be read. And while we often think of the Ice Age as a time long past, it's worth remembering that we are still technically in an ice age. We're just in a warmer phase, a relatively cozy interglacial period known as the Holocene. The glaciers may have pulled back, but they haven't disappeared entirely. Greenland and Antarctica still hold vast reservoirs of ice, remnants of a time when cold ruled the Earth. So as you rest tonight, picture a world of snowfields stretching to the horizon, of mammoths marching beneath low winter suns, of humans huddled in firelit shelters dreaming of spring. The Ice Age is not just a distant chapter, it's a part of our story, carved into our landscapes, buried in our bones, and echoing quietly in the frost that still lingers on mountaintops. Imagine standing at the edge of a vast, icy plain. The wind bites at your face and the ground crunches beneath your fur-wrapped boots. In the distance, mammoths trudge through snow, their breath steaming in the cold air. You grip a stone-tipped spear in your hand, not just for hunting, but for survival. This isn't a scene from a movie. For our ancient ancestors, this was daily life. Surviving the Ice Age wasn't just about battling the cold, it was about adapting to an ever-changing environment filled with challenges, from shifting landscapes and migrating animals to unpredictable weather and dwindling resources. And yet, through it all, humanity endured. More than endured. We innovated, we travelled, and we formed the roots of the cultures we know today. Let's take a closer look at how humans survived, and in many ways thrived during the Ice Age. First, shelter. Staying warm was a matter of life and death. In colder regions, early humans built shelters from whatever materials they had available. In the mammoth steppe of Europe and Siberia, some communities constructed homes out of bones and tusks of the very creatures they hunted. These bone frameworks were then covered in hides and packed with snow or earth for insulation. It wasn't glamorous, but it worked. A well-insulated shelter could keep out the biting wind and trap heat from fire and body warmth. Speaking of fire, controlling it was a turning point in human evolution. Fire provided warmth, of course, but it also brought light, protection from predators, and the ability to cook food. Cooking made meat and plants easier to digest and more nutritious. It also helped people bond, gathering around a fire for warmth and storytelling, building community in the midst of an otherwise harsh world. Clothing was another key to survival. While we often imagine early humans dressed in rough, ragged hides, there's evidence that Ice Age clothing was surprisingly sophisticated. People learned to tan animal skins, sew garments with bone needles, and layer materials for insulation. The development of tailored clothing was essential, especially in places where temperatures could plummet well below freezing. A carefully crafted fur coat wasn't just a fashion choice, it was a lifeline. And then there's food. Ice Age diets were diverse and heavily dependent on location. In the colder regions, large game provided the bulk of nutrition. Mammoths, bison, reindeer, and woolly rhinoceroses were hunted using coordinated group strategies. Early humans weren't just scavengers, they were skilled hunters, working together with tactics passed down through generations. In coastal areas or near rivers, people fished and gathered shellfish. In warmer zones, where vegetation was more abundant, they collected nuts, berries, roots, and edible plants. This diet required deep knowledge of the landscape, knowing which plants were edible, which were poisonous, and when to harvest them. In some areas, humans even stored food in cold natural spaces, essentially inventing the original freezer. But Ice Age survival wasn't just about physical needs, it was also about mobility. The climate was unpredictable, and as ice sheets advanced or retreated, animals migrated and ecosystems shifted. Humans had to follow. This meant being constantly on the move, often walking for hundreds of kilometers across difficult terrain. But it also meant discovering new lands, encountering new environments, and adapting to unfamiliar challenges. One of the most remarkable migrations in human history occurred during the Ice Age, the movement into the Americas. As sea levels dropped, the Bering Land Bridge between Siberia and Alaska was exposed, creating a corridor for humans and animals to cross. We believe that sometime between 25,000 and 15,000 years ago, small bands of humans made their way across this bridge. From there, they spread southward, populating the continents over thousands of years. This kind of migration wasn't done lightly. It required knowledge, planning, and trust in the skills that had been passed down. It also meant adapting to new animals, new climates, and new threats. But humans have always been explorers at heart, and the Ice Age gave us both the need and the opportunity to explore on a global scale. And while we're on the topic of skills passed down, let's talk about culture. The Ice Age wasn't just a time of bare survival. It was also a time of creativity and expression. In caves across Europe and Asia, we find extraordinary examples of early art, paintings of animals, handprints, and symbolic shapes made with natural pigments. These images weren't created out of boredom. They likely held deep meaning, religious, spiritual, or practical. Some may have been part of rituals, others may have served as storytelling tools or markers of memory. Whatever their purpose, they show us that Ice Age humans were thinkers and feelers. They imagined, they dreamed, and they shared their inner worlds with others. Music also likely played a role. Archaeologists have found flutes made from bird bones and mammoth ivory. Simple instruments, but enough to produce melodies that might have echoed through icy valleys or flickered caves. In a world of uncertainty, song and rhythm may have helped people bond, celebrate, and mourn. Language, too, was critical. While we don't have a fossil record for spoken words, the complexity of Ice Age tools, hunting strategies, and cultural practices suggests that language was already well developed. Communication would have been essential, not just for coordinating a mammoth hunt, but for teaching, storytelling, and sharing knowledge across generations. And then there's the question of belief. Did Ice Age humans worship gods? Did they believe in spirits? We can't say for certain, but we can say that they buried their dead with care, sometimes with tools, ornaments, or food for the journey beyond. These burials suggest respect, remembrance, and possibly a belief in an afterlife. Even in the coldest, hardest times, there was a space for reverence. One of the most enduring legacies of the Ice Age is resilience. Human beings were not the strongest animals. We didn't have fur to protect us, claws to hunt with, or wings to escape danger. But we had something else: adaptability, the ability to learn, to innovate, and to pass on knowledge. These traits allowed us to survive not just the physical challenges of the Ice Age, but also the emotional and social ones. And so, from the biting cold of the Mammoth Steppe to the rain-shadowed valleys of glacial Europe, humanity persisted. We stitched clothes from skins, chipped tools from stone, painted dreams onto cave walls, and walked farther than any other animal had before us. As you drift off tonight, picture yourself beside a fire under the Ice Age stars. The cold is just outside, but you are wrapped in warmth. You hear the quiet hum of conversation, the soft rustle of fur, the distant call of an owl. You're not alone. You're part of a story, one that stretches back tens of thousands of years to a time when every breath was a victory and every step forward shaped the path of all who would follow. The world did not thaw overnight. After tens of thousands of years under the cold grip of the last glacial maximum, the planet began to warm, but slowly, cautiously, like a great bear waking from hibernation. The process was not smooth, nor was it without drama. Earth's transition out of its most recent glacial period was a journey of fits and starts, floods and fires, extinctions and rebirths. It was a time of massive change, not just in temperature and sea level, but in the very fabric of the biosphere. Let's begin around 20,000 years ago. At this point, the ice sheets were at their greatest extent. North America was blanketed by the Laurentide ice sheet, a massive dome of ice thicker than two Empire State Buildings stacked end to end. Europe bore the weight of the Fennoscandian ice sheet, which stretched across the British Isles, Scandinavia, and deep into what is now Russia. Sea levels were more than 100 meters lower than today, exposing vast plains and connecting continents. It was a cold, dry, and windswept world. But things were beginning to shift. Summer temperatures in the northern hemisphere began to inch upward, driven by the subtle pull of the Milankovitch cycles, the same cosmic rhythms we explored earlier. More solar energy reached northern latitudes during summer, causing glaciers to melt a little more each year than they grew in the winter. That tiny imbalance, repeated year after year, began the long process of deglaciation. As the ice melted, landscapes were transformed. Rivers of meltwater poured off the glaciers, carving valleys and forming massive lakes. One of the most dramatic examples was Glacial Lake Agassiz, which at its peak covered parts of what are now Manitoba, Ontario, Minnesota, Irma, and North Dakota. It was larger than all of the Great Lakes combined, an inland sea held back by nothing more than walls of ice and earth. Eventually those walls gave way. The collapse of glacial dams led to sudden, catastrophic floods. These mega-floods sent torrents of water rushing across the land, reshaping entire regions in a matter of days. In North America, one such flood may have occurred when Lake Agassiz burst through into the Atlantic Ocean, releasing thousands of cubic kilometers of fresh water into the sea. This sudden influx disrupted ocean currents, particularly the Atlantic meridional overturning circulation, which plays a crucial role in distributing heat around the planet. And just like that, the warming trend faltered. Around 12,800 years ago, the planet entered a sudden cold snap known as the Younger Dryas. Temperatures in parts of the northern hemisphere plummeted back to glacial levels in a matter of decades. For about 1,200 years, the Earth seemed to pause in its thaw, as if unsure of whether to go forward or backward. The causes of this abrupt cooling are still debate. Some blame meltwater disrupting ocean currents. Others suggest a comet or meteor impact, or perhaps a massive volcanic eruption. Whatever the trigger, the effect was clear. Glaciers re-advanced in some areas, and the global climate cooled sharply. For the people and animals alive at the time, the Younger Dryas was a jarring reversal. Plants that had begun to spread suddenly struggled to survive. The reappearance of colder, drier conditions put pressure on both ecosystems and early human societies, yet once again, life endured. Then, around 11,700 years ago, the cold spell ended just as quickly as it had begun. The climate warmed, and this time it stayed warm. We entered the Holocene, the current interglacial period, and the last remnants of the great ice sheets began to fade. Sea levels rose dramatically, coastlines flooded, entire regions disappeared beneath the waves. Places that had once been dry land, like Doggerland, the land bridge between Britain and mainland Europe, were gradually swallowed by the sea. This rising tide likely had profound effects on human populations, prompting migrations, the reshaping of communities, and perhaps even the first legends of floods in ancient storytelling traditions. At the same time, ecosystems shifted. The tundra that had dominated much of the northern hemisphere gave way to forests. Animals adapted to the cold, such as mammoths and woolly rhinos, began to disappear. Some populations held on in isolated pockets for thousands of years, but eventually most of the great Ice Age megafauna went extinct. The exact causes remain a subject of intense debate. Climate change certainly played a role, but so did humans, whose hunting practices may have accelerated the decline of already stressed species. In the newly thawed world, humans began to flourish in new ways. The stability of the Holocene climate allowed for something revolutionary: agriculture. Instead of constantly moving in search of food, people could now settle in one place, plant crops, and domesticate animals. This marked the beginning of civilization as we know it. Villages, cities, writing, trade, and it all unfolded on landscapes that had been shaped and sculpted by ice. Glaciers left behind rich soils, broad plains, and freshwater lakes. They carved river valleys and deposited minerals that would one day support agriculture and industry. Even the shape of continents and coastlines as we know them today is the result of glacial activity and post-glacial flooding. Without the Ice Ages, the world would quite literally look different, and in some ways, we're still living with its legacy. Greenland and Antarctica remain cloaked in ice, holding enough frozen water to raise sea levels by tens of meters if fully melted. Permafrost still clings to northern Canada, Siberia, and Alaska, and every winter snow still falls where glaciers once ground rock into fine powder. More subtly, the memory of the ice lingers in our myths and imaginations. Many cultures have legends of great floods, endless winters, or a time when the world was covered in snow. These stories, passed down through generations, may echo real memories daily of the Great Thaw, tales first told around firelight by those who watched the ice retreat and the oceans rise. So tonight, as you settle into sleep, imagine the slow drip of melting ice. Picture the rivers swelling, the forests creeping northward, the mammoths wandering their final trails. Imagine the people who stood on the edge of the frozen world and watched it change, who adapted, moved, and began again. The end of the Ice Age was not just the end of something, it was the beginning of the world we now call home, a world warmed, reshaped, and reborn. Even though the great ice sheets have long since melted from much of the world, the legacy of the Ice Age lingers all around us, in the air, the land, and even the water we drink. Today, high atop the coldest places on Earth, the remnants of that ancient frozen world remain, tucked away in glaciers that still grind their way across mountaintops and polar regions. These glaciers are more than just scenic features or icy vacation destinations for adventurous mountaineers. They are natural time capsules, quiet archivists of the planet's past, and increasingly messengers about its future. Let us begin in Greenland, a vast island blanketed by one of the two major ice sheets left on Earth. The Greenland ice sheet is an enormous body of ice, stretching over 2,000 kilometers from north to south and covering roughly 80% of the island's surface. At its thickest point, it reaches more than 3 kilometers deep, so much ice that if it were to melt completely, sea levels around the world could rise by more than 7 meters. And then there's Antarctica, the grand titan of ice. The Antarctic ice sheet is the largest single mass of ice on the planet. It holds nearly 90% of the world's freshwater ice and covers an area more than 1.5 times the size of the United States. If all of Antarctica's ice were to melt, sea levels could rise by over 60 meters, enough to drown many of the world's coastal cities and transform maps beyond recognition. But these icy regions are not static. They flow, shift, and respond to changes in temperature and snowfall. Glaciers move, albeit slowly, like rivers of frozen time, grinding rock beneath them into fine dust and carving valleys as they go. This movement helps shape the land, creating features like U-shaped valleys, moraines, fjords, and kettle lakes. In places like Alaska, the Alps, the Himalayas, and Patagonia, smaller alpine glaciers still snake down mountainsides. These are what most people picture when they think of glaciers, blue-tinged giants crackling and creaking under the sun. Many of these glaciers are shrinking, retreating upslope year after year, leaving behind exposed rock and empty valleys. Scientists watch these glaciers closely because they offer some of the clearest visual evidence of a changing climate. But glaciers are more than just indicators of temperature. They're storytellers. Deep within the ice, trapped air bubbles preserve tiny samples of Earth's ancient atmosphere. When scientists drill into ice sheets, sometimes to depths of more than 3 kilometers, they retrieve long cylinders called ice cores. These cores are like time machines, allowing researchers to examine the composition of the air, the presence of volcanic ash, dust, and even pollen from tens of thousands, or even hundreds of thousands, of years ago. By studying ice cores from Greenland and Antarctica, scientists have been able to reconstruct a remarkably detailed record of Earth's climate history. They can see past glacial and interglacial cycles, detect major volcanic eruptions, and even pinpoint periods when greenhouse gas concentrations rose or fell dramatically. Some ice cores contain layers dating back over 800,000 years, a nearly unimaginable time span, all captured in frozen water. One of the most striking things these ice cores reveal is how tightly linked carbon dioxide levels are with global temperatures. When carbon dioxide is high, the planet warms. When it is low, the planet cools. During the last glacial maximum, for example, atmospheric carbon dioxide levels were around 180 parts per million. During the warmer interglacials, levels rose to around 280 parts per million. Today, human activities have pushed that number past 420 parts per million, higher than anything seen in at least the past 800,000 years. Glaciers also play a vital role in the water cycle. Many major rivers, such as the Ganges, the Indus, and the Yangtze, are fed by meltwater from glaciers in the Himalayas. These rivers support hundreds of millions of people, providing water for drinking, agriculture, and industry. As glaciers retreat, the timing and quantity of meltwater changes, potentially disrupting these life-sustaining systems. Another important aspect of glaciers is their albedo, how much sunlight they reflect back into space. Fresh snow and ice are highly reflective, bouncing solar energy away and helping to keep the planet cool. As ice melts and darker land or ocean is exposed, more sunlight is absorbed, leading to further warming. This creates a feedback loop. Warming causes melting, which causes more warming. It's a delicate balance, and one that is being tipped. Glaciers are also cultural icons. For many indigenous communities, they hold spiritual and historical significance. In the Andes, glaciers are seen as sacred ancestors, guardians of the land and water. In Tibet, the glaciers of the Himalayas are sometimes called the third pole, a source of life and wisdom. As these icy sentinels shrink, the loss is not just environmental, it is emotional, spiritual, and cultural as well. And yet, there is a quiet wonder in standing before a glacier, listening to it crackle and sigh under the sun. These ancient masses have seen more than any civilization, more than any city or monument. They've survived eruptions, ice ages, and mass extinctions. Their melting now is not the end of time, but a reminder of time's passage, a slow, patient signal that even the most immovable things can change. The study of glaciers also brings people together. Teams of glaciologists, climatologists, geologists, and even artists collaborate across borders to explore, measure, and document the world's remaining ice. From drones that map crevasses to satellite imagery tracking retreat, the science of glaciers has become a global effort to understand the past and prepare for the future. It's easy sometimes to feel overwhelmed by what glaciers seem to tell us. Stories of warming seas, rising tides, and shifting climates. But there is also a quiet resilience in their slow persistence. Even in retreat they teach, even in melting they reveal. Their lessons are layered, like the strata of ice they hold within, patient, ancient, and wise. So tonight, if your thoughts drift to distant mountains or snowy poles, imagine those slow-moving rivers of ice inching across time. Imagine the quiet pressure of centuries, the creak of frozen layers settling in the dark. Picture the bubbles of ancient air, trapped like whispers in crystal. They've waited hundreds of thousands of years to speak, and now they are speaking, in soft cracks and flowing meltwater, in shifting coastlines and changing weather, in stories frozen in time now warming into motion. When we think of the Ice Age, we often imagine a world of mammoths and glaciers, of frozen valleys and snowbound forests. But the legacy of that ancient cold runs deeper than geology or biology. It also left its mark on the human imagination. Long after the ice began to retreat, its echoes continued to shape myths, folklore, art, and memory. The story of ice is not only written in stone and bone, but also whispered in tales passed down through generations, etched into our cultures as clearly as it is carved into the land. In many ancient traditions, there are myths of long, endless winters, times when the sun faded, the earth froze, and life itself was threatened by cold and darkness. These stories likely carry fragments of real remembered experience. For those living through the final phases of the last glacial period, the world would have seemed perilous and shifting. Seasons were less predictable, summers could be cool and brief, the boundary between survival and extinction was thin. The Norse sagas tell of Fimbulvita, the great winter that would precede the end of the world. In this myth, 3 years of unending snow and bitter cold cover the earth, weakening gods and mortals alike before the final battle of Ragnarok. Scholars have long wondered whether this idea of a mighty winter was inspired, in part by cultural memory of post-glacial hardships or volcanic winters. After all, stories often exaggerate, but they rarely come from nowhere. Other cultures too speak of great freezes or floods, of times when the earth was reshaped by vast forces. In the legends of the Pacific Northwest's indigenous peoples, there are stories of great floods sweeping across the land, eerily similar to what we now know as glacial lake outburst floods. In parts of Siberia and Mongolia, traditional tales describe the spirits of the cold, powerful beings who control snow and ice, demanding respect and caution. In some Inuit stories, the land itself is alive, the ice watching, listening, waiting. These myths didn't just serve as entertainment, they were a form of cultural memory, stories as survival tools. When a tale warns of a winter so long that fires cannot keep you warm, it's also teaching resilience. When a story speaks of navigating by the stars to escape the advancing ice, it's embedding navigation skills in narrative. And when a myth says that the earth has changed before, it plants the seed of adaptability. Ice may have tested our ancestors, but it also taught them. The memory of cold shows up not just in myths, but in more recent cultural expressions too. The Romantic poets of the 19th century, for example, often drew inspiration from icy landscapes. William Wordsworth described glaciers and snow-covered mountains with awe and reverence. Mary Shelley, during the famous Year Without a Summer in 1816, a volcanic winter caused by the eruption of Mount Tambora, penned Frankenstein, whose bleak, wind-swept Arctic settings may have been influenced by the unseasonal chill surrounding her. Even in fairy tales, the Ice Age leaves traces. Think of the Snow Queen ruling her frozen palace, her breath turning the world white, or the enchanted winter that locks entire kingdoms in sleep. These aren't just metaphors, they're echoes. The imagery of cold as both beautiful and dangerous runs deep through our storytelling traditions. Ice is mystery, it is silence, it is power, and then there's art. Prehistoric humans living in the shadows of glaciers still found time to create. In caves across France and Spain, in places like Lascaux and Chauvet, stunning images of Ice Age animals cover the walls. Bison, reindeer, lions, mammoths, all painted with care, skill, and astonishing grace. These weren't idle doodles, they were cultural expressions, rituals, memories, messages to future generations. In a world of constant challenge, people made time to remember, to record, to make beauty. One of the most remarkable discoveries in recent decades was the so-called Venus figurines, small sculptures of women carved from stone, ivory, or bone, dating back more than 20,000 years. Found across Europe and Asia, these figures may have had religious, symbolic, or even educational roles. Some scholars speculate they represent fertility, survival, or the ideal human form in a world where body fat was a blessing in the cold. Whatever their meaning, they show that even in a harsh world of snow and scarcity, humans valued art and symbolism. As the ice retreated and human societies became more settled, these ancient memories began to take new forms. In architecture, cold was something to be held at bay, hence the thick stone walls, the hearth-centered homes, the cloaks and layers worn even indoors. In literature, winter was often the season of death and silence, the backdrop to reflection or despair, yet always there was the promise of spring. This cyclical understanding of time, winter leading to renewal, may well have its roots in the long winters and slow thaws of the Ice Age. Even today, our relationship with winter carries deep psychological weight. Snow still inspires awe. Ice still brings both danger and wonder. Skiers chase the cold up mountains. Artists carve sculptures from frozen water. Photographers wait for frost-covered branches to catch the morning light. And in colder parts of the world, the return of the sun after a long winter night is celebrated with festivals, bonfires, and light. Perhaps most poignantly, we now live in a time when the cold is retreating again, but not on its own terms. Glaciers are melting not because of orbital cycles or tectonic shifts, but because of human activity. The stories we tell now are no longer just about surviving the ice, they're about preserving what's left of it. Documentaries show the cracking of ice shelves. Poets write elegies for disappearing snowfields. Children read stories about polar bears and penguins, animals whose homes are vanishing. And still, there's hope. The same ingenuity that helped humans survive the Ice Age, crafting tools, building shelters, telling stories, may yet help us respond to the challenges ahead. We are still a species shaped by ice, even if we now shape it in return. And just as the myths of the past held lessons for survival, perhaps the stories we tell today about melting glaciers, changing seasons, and the beauty of frozen places will help guide future generations. So as you lie in the quiet of night, picture the tales told long ago around a fire, as frost curled at the edges of fur tents and stars glimmered through the cold. Stories of endless winters, of spirits in the snow, of brave journeys through ice-bound lands. Stories that warmed hearts even as the world froze. In every flake of snow there is a memory. In every frost-covered branch a whisper of ancient cold. And in every story of ice a reminder that we have faced the chill before, and we will face it again, not with fear but with wonder. And so our journey through the frozen chapters of Earth's history comes gently to a close. From a world locked in ancient ice to the slow, patient thaws that shaped our landscapes and our species, we've wandered through deep time, glacial rhythms, mammoth migrations, and the quiet stories told by snow and stone. The Ice Age wasn't just a period. It was a sculptor, a teacher, and a stage on which the drama of life unfolded in silence and frost. What began as cold and forbidding slowly transformed into fertile valleys, flowing rivers, and the foundations of civilization. And even now, in our modern world of glowing screens and central heating, the echoes of those frozen epochs remain, in the shape of the land beneath our feet, in the myths we tell, and in the very water we drink. If you're still awake, thank you for traveling with me tonight. If you've already drifted off, I hope your dreams are full of quiet snowscapes and ancient stars. Either way, before we part, let me ask again, where are you listening from? And what time is it where you are? Whether it's the middle of the night, early morning, or somewhere in between, I'd love to know. And if this gentle journey through Earth's icy past brought you comfort or curiosity, please consider leaving a like, or even subscribing to The Sleepy Scientist. It helps more dreamers find their way here, and it means the world to me. Until next time, sleep well, stay warm, and remember, this planet of ours has endured fire and frost, silence and storm, and through it all, life found a way. So whatever tomorrow brings, you are part of that great ongoing story. Good night.